In a previous video, we saw how just by using two pieces of glass, we can magnify things which are very far away. In other words, build a telescope. In this video, let's figure out the magnification or the magnifying power of this telescope. We usually define the magnification as the angle subtended with the telescope at our eye to the angle subtended by the object without the telescope. So with the telescope, you can see that the angle subtended by this is this angle. Let me make that moon a little bit thin so that we can see that angle better. All right, there we have it. The moon is fine, but I'm just making it thin so that we can draw the angles nicely. So this is the angle subtended at our eye right now. Let's call that angle as theta prime. All right. And what would have been the angle subtended by the moon if we hadn't used the telescope? Well, if we hadn't used the telescope, the angle subtended would be, these rays would be directly falling on our eyes, right? If we hadn't used the telescope. So the angle subtended would be just this. Let's call that as theta naught. Let's call it theta naught. And so the ratio of these two angles will be the magnification produced by the telescope. And why are we taking the ratio of the two angles? Well, we've seen before, because the angle is what decides what the height of the image in our retina is, or how big it looks like. So the ratio of this angle is really the ratio of the image size in our retina. Again, we've talked about this before. All right, now you can go ahead and pause the video and see if you can somehow look at this diagram and figure out what this ratio is. Just give it a try. All right, let's see. Theta prime is this number. That can be figured out by looking at this triangle. We can use tan theta is equal to theta approximation. So if you take tan ratio, it's the height of the moon. Let's call it as the height hi, because it's the image, height of the moon, divided by the adjacent side, which is the focal length of the eyepiece. Divided by, what is theta naught equal to? Well, instead of taking theta naught over here, we can calculate theta naught over here. Can you see they're the same angles? They're vertically opposite angles. Right. And so we could now take this triangle and figure out what theta naught is using the same approximation. So again, it will be the opposite side, h of I, divided by the focal length of the objective. And so if you simplify this, the height of the image cancels out. And as a result, we now get the magnification. We'll write that over here. The magnifying power of our telescope turns out to be the focal length f naught of the objective divided by the focal length of the eyepiece. So this means to get the maximum out of our telescope, we need to have a very high focal length objective and a very low focal length eyepiece. All right, one super duper last thing is I was always confused with this ray diagram. You see, whenever someone would say that the rays of light are coming from far away, I would always have this picture in my mind. So I would always think that the rays of light coming from infinity would form point images. But over here in a telescope diagram, it's not a point image. Why is that? And for that matter, it didn't make sense to me why the magnification depends on the focal length of the objective. Because I would think that if the focal length increases, well, the rays of light will get focused far away, but it would still be a point image, right? I mean, why would it depend on the focal length of the objective? So what's going on? Well, what's really going on is that this is just an approximation. You see, in reality, whenever rays of light are coming from far away from any source, those rays of light in reality are not parallel to the principal axis. They're parallel to each other, as you've seen over here, but they're not in general parallel to the principal axis. They do form a small angle, which we're calling as theta naught, with the principal axis, which is approximating in most cases. I think till now, in most cases, we approximate that angle to be just 0 because we don't care about the image size, but it's not 0. And as a result, the image size that we're forming also has a finite size. It's not really 0, but it is a point image in the sense that it is much smaller than the actual size of the moon. The moon is thousands of kilometers across, right? This is like a few centimeters maybe. So it is a point image, but it's not point size like this. So we have to get rid of this approximation. And as a result, if you look carefully, what do you think will happen now if we were to increase the focal length? If we were to increase the focal length, this principal focus would be somewhere over here, and the blue ray would come from here. It would hit the lens somewhere over here. And now, can you see the two rays would now meet up somewhere over here? Let me just show you that. Here it is. Just take a look at this. If the focal length was larger, can you see that this ray and this ray are now meeting somewhere farther away? And not just that, the image size as a result would be bigger. So something that we miss out in this approximation is that the image that we're getting really depends on the focal length. Bigger the focal length, see over here, bigger the focal length, bigger is the image size. This is so important. Let me just show you that quickly. Again, when we're looking at our moon, if we use a high focal length objective, the one we used in the demo actually, look at the size of the image formed. Now compare this to what will happen if we use a low focal length objective. This is a low focal length objective. Can you see that the image size is much smaller now? In both cases, rays of light are coming from infinity. They're being focused at their respective principal foci. Yet, the size of the image, it depends on the focal length. And it's for that reason, bigger the focal length, bigger will this image size be, making this angle bigger, and so more magnification. And for the eyepiece, well, if the eyepiece focal length is smaller, then you can go closer. And that's why smaller the eyepiece focal length, more the magnification. So the key takeaway is that in any telescope, the objective's purpose is to bring the object closer, and the eyepiece, the purpose of the eyepiece is to magnify that image, just like a simple magnifying glass. Also, in any telescope, the objective is usually made very large so that it can capture a lot of light, and so the image will be nicely illuminated so that we can see it clearly.